In class 13, we have seen Kirchhoff's current law and Kirchhoff's voltage law, and I have applied and sign conventions. And I have taken that, and I have taken sign conventions. And case is in accordance with the law of conservation of charge, and KVL is in accordance with the law of conservation of energy. Okay. Now let us say, I told you in the class 12, I think, a grouping of cells. I have given directly an expression. I told you in that class, I will definitely derive that expression when we come to the Kirchhoff's laws. Now I will do that one. What is circuit is, here we have taken this one. Internal resistance is R, cell of EMF E. Internal resistance is R, cell of EMF E2. This is connected to an external resistance R. The current I is flowing like this. Current I is flowing like this. Current I is flowing like this. Now at this junction, current will split. Therefore, the current here is I1. Current here is I2. So that I is equals to I1 plus I2. Again, this current is I1. This current is I2. Current is I1 and current is I2. I directly given expression that the current I is equals to E1 R2 plus E2 R1 by R1 R2 plus capital R into R1 plus R2. If you check my lecture 12 in parallel grouping of different EMFs, I have derived the expression. I have given you directly the expression. So the current I is equals to E1 R2. This is, let us take it as R1. This is take it as R2. E1 R2 plus E2 R1 by R1 R2 plus capital R into R1 plus R2. Now let us, I told you on that day only, I will definitely derive this one. Now I am deriving that one also after explanation of Kirchhoff's laws in class 13. Now let us take it as A, B, C, D. Okay, A, B, C, D. A is, now take it, this is B. A, B, C, A, B, C, D. This is A, B, C, D. This is taken as E. This is F. This is G and H. Let's take like this. Now apply KVL. KVL to A, B, C, D, H, G, A. A, B, C, D, H, G, A. H, G, A. Remember, now in this loop, I am not taking this one. I am not taking AFE, AFED. I am taking ABCD, HGA. ABCD, HGA loop I am taking. Now apply KVL. KVL to, now this one. So we are moving like this. We are moving like this, and there is a, here what is it? There is a drop in the potential. There is a, we are moving like this. A to B, we are moving. The drop in the potential. Therefore, minus of E1. Drop in the potential. And we are moving like this. Current I1 is opposing. Therefore, it is taken as a positive. Plus. Current is opposing. Are moving like this. Current is coming like this. Therefore, plus I1 R1 and A, B, C, D, H. The current like this. No, this is like this. No. A, B, C, H, and we are moving HGA. Current, we are moving like this. We are moving like this. Therefore, again, the current, what is the current here? The current is I. Same current, no? The current is I. The current I is again opposite. We are moving from DHGA. Current is opposing. Therefore, plus IR is equal to 0. Minus of E1 plus I1 R1 plus IR is equals to 0. Okay. From this equation, what is I1? Implies I1 R1 is equals to E1 R1 is equal to E1 minus of IR. This implies I1 is equals to E1 by R1 minus of IR by R1. Say equation 1. I1 is equals to E1 by R1 minus of IR by R1. Say equation 1. Now let us apply KVL. KVL to the loop AFED, HGA. AFED, HGA. We are taking the upper loop now. Now take the lower loop now. AFEDHGA. Now again apply the KVL. What do we have? Again, we are moving like this. There is again, we are moving like this. Drop in the potential. This is positive, negative. This is positive, negative. Drop in the potential. Minus of E2, minus of E2. We are moving like this. Current I2 is opposing. Therefore, plus I2 R2 plus I2 R2. We are moving like this. Again, current is opposing as moving from H to G. Therefore, plus IR is equal to 0. This implies I2 R2 is equals to E2 E2 minus of IR. This implies I2 is equals to E2 by R2 minus of IR by R2. E2 by R2 minus of IR by R2. This implies, say, equation 2. Now, what is the total current? The total current I is splitting into I1 and I2. Again, this same current is these I1 and I2 are combining and coming back. Therefore, see, this is combining and again coming back. Sorry, this I1 and I2 coming again. They are coming back. Therefore, what happens here? I is equals to I1 plus I2. I is equals to I1 plus I2. I is equals to I1 plus I2. See, I is splitting into I1 plus I2 and I1 and I2 are combining to give current I. Therefore, 3 plus 2 is equals to 5. 3 plus 2 is equal to 5. 5 is equal to 3 plus 2. Like that it is splitting. Now, I is equals to I1 plus I2 implies I is equals to, this is equation 3. Now, put 1, 2 in 3. Put 1, 2 in 3. Implies I is equals to I1 is equals to E1 by R1 minus of IR by R1 plus I2 is E2 by R2 minus of IR by R2. This implies I is equals to E1 by R1 plus E2 by R2 minus of IR. If you take common IR and IR, minus of IR common, we get 1 by R1 plus 1 by R2. Now take this, here I is here I is there. Bring this side to this side. This implies I into, one more step, I plus IR into 1 by R1 plus 1 by R2 is equals to E1 by R1 plus E2 by R2. Implies I take common 1 plus R into 1 by R1 plus 1 by R2 is equals to E1 by R1 plus E2 by R2. This implies I into 1 plus R into R1 plus R2 by R1 R2 is equals to E1 R2 plus E2 R1 by R1 R. Take LCM. This implies I into R1 R2 plus R into R1 plus R2 is equals to E1 R2 plus E2 R1 by R1 R2. Sorry, by R1 R2. Okay. Now this is left hand side R1 R2, right hand R1 R2 gets cancelled. This is equal to. Therefore, left side R1 R2 gets cancelled. This implies I is equals to E1 R2 plus E2 R1 by R1 R2 plus R into R1 plus R2. That is the expression for current. This is very important equation in solving problems in the JEE main. This is very important. Very important expression. So you should get, remember, if you cannot do this all type of derivation in the examination or the main examination. Therefore, you have to remember this. If the circuit is like this, then the current I is equals to E1 R2 plus E2 R1 by R1 R2 plus R into R1 plus, or just we had applied the KVL to this loop and KVL to this loop, and we equate the current I is equals to I1 plus I2 and get the value of current I. Sometimes the circuit will be like this. This circuit is changed like this. To confuse you, the circuit may be changed like this. To confuse the students, circuit will change like this. Sometimes it may be given Now what is the current? We asked to find what is the current. The circuit is like this, no? So we derive for this circuit. The current is I here, R here, R1, R2, and the current I is flowing like this. This is I1, this is I2, and this is I1, this is I2. So the currents are I1, this is E1 R1, this is E2 R2. Now what is you asked to find what is the current? Then or else will be given like this. We will be given like this also. No changes here. We will be given like this. Then you have to go with the same expression only. So sometimes we will be given like this. It may be given like this also. Sometimes we will be given like this. There are different ways of expression like this. See, this is between these 2 points, no? So between these 2 points, again we can take circuit as like this. You may given like this also. Then also same expression. What is the current here? So this is I1, this is I2, same. E1 R2 plus E2 R1 by R1 R2 plus R into R1 plus R2. So for confusion's sake, this may be given outside or may be given inside. This R may be given inside or R may be given outside, but same expression is valid. Okay. Now let us see Wheatstone bridge. Now let us see Wheatstone bridge. Wheatstone bridge. Wheatstone bridge is a sensitive instrument used to measure the unknown resistances, very small resistances, very accurately. Wheatstone bridge is a very sensitive instrument. Why we are calling it sensitive? Means we can measure the small amounts of resistors also. That's why we can call it as a sensitive device or instrument. Therefore, Wheatstone bridge is a sensitive instrument used to calculate the unknown resistance more accurately and also to compare the two resistances Now let us see what is Wheatstone bridge. Consists of 4 arms. 4 arms in the form of a bridge. This is one arm. This is another arm. This is one arm. This is another arm. This is A, B, C, D. Let us say P, Q, R and S. P, Q, R and S. This is like a 4 resistor current in the form of a bridge. Across one diagonal we connect a galvanometer. Across one diagonal we connect a galvanometer whose resistance is G. G is galvanometer. Here G is galvanometer. Galvanometer resistance is G. Resistance is G. So what is a galvanometer? A galvanometer again a device used to measure the small amounts of currents. Galvanometer again is a sensitive device used to measure the small amounts of currents or charges of the order of 10 power minus 6 amperes. Very small amounts of current we call it as a galvanometer. High amounts of current we call it as a ammeter. Ammeter measures high currents. Galvanometer measures low currents of the order of 10 power minus 6. Therefore, it is a current measuring device which measures small amounts of currents. And this is G. Now, and here to one diagonal BD we connected a galvanometer. Another diagonal we connected a. This is plug key. There is no need. No need. This is a EMF E. This is EMF battery of EMF E. So across one diagonal BD we connected a galvanometer. Across another diagonal we connected a battery of EMF E volts. Now the current I is flowing like this. It splits into 2 parts. Here current I1. This is current I2. Current I1. This is current I2. Let the galvanometer current is Ig. Current through the galvanometer is, let us take it as Ig. You can take direction like this or you may take direction like this, no problem. You will get the same answer. Now let the current through here is I3 and current through this branch is, let us take it as I4. Generally if we take, if I1 is flowing like this, it is split into I3 and IG. Therefore I3 can be taken as, generally I3 can be taken as I1 minus IG, because 10 is flowing like this, it is splitting into 4 and 6. 4 and 6. Therefore this 4 is equals to 10 minus 6 only. Therefore, if the I1 is flowing like this, then the I3 is equals to I1 minus the junction. Apply junction law here. I1 towards junction, IJ, I4, away from the junction. Therefore, I1 is equals to I3 plus IG only, like that. Okay. Similarly, I4 is equals to, what is I4? IG plus I2 is equal to I4. IG plus I2 is equals to I4. So IG is coming like this, I2 is coming towards junction. IG plus I2 is equals to away from the junction, I4. So you can use this. Okay. Now apply KVL. Apply. So galvanometer is Wheatstone bridge. It is consists of 4 ohms of resistors. PQRS are resistors. PQRS are resistors. PQRS are resistors. G is the galvanometer whose resistance is also G. To take it as galvanometer resistance as G. Now across one diagonal we connected a galvanometer of resistance G. Across another diagonal we connected a battery of EMF E volts. Now apply what do you call this, KCL at B. KCL at B. So what we have taken? I1 is towards junction. I1 towards the junction. I1 is flowing towards the junction. And IG away from the junction. Therefore minus of IG. Minus of IG. I3 away from the junction. Therefore minus of I3 is equal to 0. Implies I1 is equals to IG plus I3. Equation 1. I1 is equals to IG plus I3. Equation 1. Similarly, so KCL at D. KCL at D. Apply the KCL to this junction D. Then what happens here? D. I2 is flowing towards junction. I2 positive. IG towards junction plus IG. IG also towards the junction D. And I4 away from the junction. Minus I4 is equal to 0. This implies I2 plus IG is equals to I4. Say equation 2. I2 plus IG is equals to I4 is equation 2. Now apply KVL. KVL to ABDA to the loop ABDA. ABDA. Apply KVL to the loop ABDA. Then AB, we are going in the direction of current. The current is also in the direction, we are moving from A to B in the direction of current. And therefore drop is negative. Drop is negative. Minus of I1P. Minus of I1P. Again in the direction of current ABDA. The direction, galvanometer also we are moving from B to D. Current is also from B to D. Therefore drop is negative. Minus of IG into galvanometer resistance G. Again from D to A. We are moving D to A. Current is from A to D. Therefore opposing. Therefore take it as a positive. Drop is positive. Plus I2R is equal to 0. Plus I2R is equals to 0. And say equation 3. Say equation 3. And or we can take it. Let me keep it aside. No problem. Next one. For the loop of BCDB. KVL to the loop. KVL, let us, or we can extend, let us simplify this one. Therefore, I1P, what is I1P? I1P is equals to IgG, I1P is equals to I2R minus of IgG, minus of IgG plus I2R, say equation 3. I1P is equals to minus of IgG plus I2R. Now, for the KVL to the loop, KVL to the loop BCDB, BC in the direction of current, drop as negative, minus of I3Q, opposing C to D, current is opposing, drop is positive, plus I4S, we are moving from D to B, current is opposing, therefore plus IgG is equal to 0. This implies I3Q is equals to I4S plus IgG. Say equation 4. This is the this is 4 equations. Now we adjust PQRS such that the current through the galvanometer is 0. Adjust PQRS such that the current through the galvanometer is 0. Such a condition is called balancing condition. I0 implies condition is balancing condition. Condition is balancing condition. Balancing condition. So for the bridge to be balanced, the current through the galvanometer is 0. For the bridge to be balanced, the current through the galvanometer should be equal to 0. Therefore, Ig is 0. Then out of the equation 1, 2, 3, 4. 1, 2, 3, 4 becomes, what are the equation 1, 2, 3, 4? 1 becomes I0 now. I1 is equals to I3. And 2 becomes I2 is equal, this is 0. This is 0. I2 is equal to I4. I2 is equals to I4. Again in this equation, this becomes 0. In the equation 3 becomes I1P is equals to I2R. And what is this equation 4? IgG. Therefore, I3Q is equals to I4S. Okay. Now divide these equations. Let us say take it as say equation 5, this is equation 6. Now what happens? 5 by 6. 5 by 6 implies I1P is equals to I2R by I3Q by I4S. But here I1 is equal to I3, this two gets cancelled. I2 is equal to I4, this two gets cancelled. Therefore implies P by Q is equals to R by S. P by R is equals to Q by S. Whatever it means, no problem. Generally we take P by Q is equals to R by S only. P by Q is equals to R by S. P by Q is equals to R by S is the condition for balancing the bridge. P by Q is equals to R by S is the condition. Ante P by Q is equals to P by Q is equals to R by S, or you can take P by R is equals to Q by S. P by R is equals to Q by R. P by R is equals to Q by S. Ratio of the resistance of these two arms will be equals to ratio of resistance of these two arms, or P by Q is equals to R by S. Anyhow, it is no problem. Now, important thing here. So if you observe these equations here, what we got? I1P is equals to I2R1. I1P is equals to I2R. I1P is equals to I2R, isn't or not? Therefore, here this bridge is balanced now. The current flowing through is 0. Therefore, if you remove this one also, no problem. We call these points B and D as equipotential points because this potential is same as this potential. I1P is equals to I2R, or I3Q is equals to I4S. I3Q is equals to I4S. Therefore, these 2 points are called as equipotential points. Now we can remove, when the bridge is balanced, the current to the galvanometer is 0. Therefore, we can remove this one. We can remove this one and we can take the circuit. We can remove this one because in a calculated resistances in many complicated circuits, we use this balancing law only. In many resistance circuits, to calculate the equivalent resistance, we consider the points as equipotential points. In such a case, we remove that resistance. We remove that point. Therefore, just like we remove this galvanometer, because the bridge for the balance in the condition, the current through the galvanometer is 0. Therefore, the current through the galvanometer is 0. Therefore, we can remove this one. If it is there or not, no problem. Okay, now this is the Wheatstone bridge. Now the important points here are, if you now in bridges, we can replace this resistances with you can also capacitors C1, C2, C3, C4. C1 by C2 is equal to C3 by C4 also. For capacitor, this variant C1 by C2 is equals to C3 by C4. Now conditions, what are the conditions? What are the important inferences from this are? Here, if you interchange this Ig here, if you put the battery here, then it makes no difference. So if the condition, if the places of galvanometer and battery are interchanged, the balancing condition does not change. First point, if you interchange the galvanometer and the battery, we put battery here and the galvanometer here, then balancing condition does not change. And also balancing condition does not depend on the magnitude of EMF. So whatever is the EMF here, balancing condition does not change. For more sensitiveness of the bridge, P should be equals to, Q should be equals to, R is equals to, yes. PQ is equals to, P is equal to, Q is equal to, R is equals to, yes. Or if you take this as 4, this is 2, this has 4, and this has 6, and this has 12. Then also this has 12, this has 12. Then P by Q, 2 by 6 is 1 by 3, R by S is 4 by 12. 1 by 3 is equal to 1 by 3. Bridge is balanced. 2 ohms, here 6 ohms, 4 ohms, 12 ohms, 4 by 12, 1 by 3, 2 by 6, 1 by 3. Bridge is balanced. Or 2 by 4, 1 by 2, 6 by 12, 1 by 2. Bridge is balanced. Now, for more sensitivity, if all are equal, this is 1, 1, 1, 1 or 2, 2, 2, 2, then it is more sensitive. But anyhow, it is no problem. And so at the balancing condition, it is taken as a null detector. We can consider this galvanometer as a null detector. We consider that galvanometer as a null detector because for the bridge balance value should be equals to 0. Now I told you that last point. I told you that so there is no difference when we interchange galvanometer and battery EMF, and whatever the EMF, it is independent. Balancing condition is independent of EMF. Balancing condition is independent of the magnitude of the EMF, and galvanometer is called as null detector. And for more sensitivity, P is equal to, Q is equal to, R is equals to, yes. And for at the balancing condition, what happens? At balancing condition, if we remove this one, if we remove it, when the bridge is balanced, no need of this galvanometer, because galvanometer current is 0. Current is 0, there is no drop across this one. No drop means this will be removed. Now, circuit like this will be like this. This is point B, this is point A, this is point C, and this is point D. Here actually we are having galvanometer here. Galvanometer between B and D we are having galvanometer. But balancing condition galvanometer is removed. Actually between B and D we are having a galvanometer here. For balancing we have removed that galvanometer. So circuit will be like this. Okay. This will be now. So what is it? Here this is P, BC, between B and C it is P, PQ, R and yes. What is equal resistance? This is series P plus Q. This is equivalent to P plus Q. This is like this. This is P plus Q. This is R plus S. R plus, these two are in series. These two are in series. R plus S. Now what is the equivalent resistance? This is equivalent to, this is equals to P plus Q parallel with R plus S. And what is the equivalent resistance? R1 R2 by R plus R2. And P plus Q into R plus S by P plus Q plus R plus S. So this is the balancing, this is the equivalent resistance, and the bridge is balanced between the terminals A and C. So equivalent resistance between terminals A and C is these two are in series, these two are in series, just like this. The circuit may be like this. So this also, if it is like this, also if you like this, this given, this also a Wheatstone bridge, but if it is balanced, then galvanometer is removed. Then P plus Q series, R plus S series, then P plus Q parallel with R plus S equivalent resistance series, P plus Q into R plus S by P plus Q plus R plus S. Let us see the next topic in the next class 15. Okay.